Okay, so up until now, we've been just really looking at the hydrocarbons, as in the compounds that just contain hydrogen and carbon atoms. But often in organic chemistry, we get some other atoms that get involved, particularly oxygen, but also nitrogen to a reasonable extent. And there's also some other ones that can tend to get involved. So, what we're going to do now is explore some of the other atoms that get involved, and that leads to things called functional groups. I'll explain to you what a functional group is, and we'll look at some of the properties of those and some reactions of just a couple of those. Next year, we do a whole lot more on these functional groups and how we make them and how we break them. Also, hopefully, you're going to see how some of this organic chemistry relates to some things that we've already done, particularly around secondary interactions and physical properties, and also related to solubility that we've also touched on earlier. Let's get into it. Okay, so there's a lot on this slide, and we don't necessarily need to recall everything on this slide this year. A lot of it is leading into what we'll do in stage 2 chemistry, and a lot of the stuff just reinforces stuff that we did on polar and non-polar and secondary interactions earlier in the year. So let's have a look at some of the functional groups that we commonly deal with, come across in organic chemistry. So the first, and it's not really a functional group, but is the alkanes, which are just the hydrocarbons, which just have carbon and hydrogen and all single bonds. Now, I think I talked about this in an earlier video, but just in case, an homologous series, a functional group, we're really using very similar terms here. The functional group, for example, here is the alcohol, so all alcohols are a homologous series. We already know that when we name alkanes, we use the ending ane. So we've got an example here, 3 carbons, so it's propane, which is the gas, the main gas in LPG. The next ones that we need to talk about are alkenes. Alkenes contain a carbon-carbon double bond. We change the ending of the name to ene. This one here, ethene, is an example of that. And we've already talked about alkenes. The next, which is a very important one, which is probably a little bit newer, is alcohols. Alcohols contain the hydrocarbon chain, like in the alkane, but somewhere on that chain they have at least one OH group. When we get this OH group, we change the ending of the name to anol, and here is our most common alcohol, ethanol. It's the alcohol in alcoholic drinks that makes you drunk. That's an alcohol. Now, another one that we'll deal with more next year, but I just want to introduce now, is this one here, where we have a carbon double bonded to an oxygen and a hydrogen, and they are called aldehydes. The last, we change the ending of the name to anal if we have an aldehyde. So here we have an aldehyde, has this carbon double bonded to the oxygen with the hydrogen. 1, 2, 3, 4 carbons, so 4 is bute, so this would be butanol. Next is ketones. Ketones are a little bit like aldehydes. They have a carbon double bonded to an oxygen, but rather than being on the end of the chain with a hydrogen, they have another alkyl chain here, so another hydrocarbon chain here. When we name those, the ending of the name becomes anone. So here we've got 1, 2, 3 carbons. It's got this ketone group, so that would be propanone. Now, propanone is much more commonly known by its common name, which is acetone, which is used for nail polish remover. Next is the carboxylic acids. They contain a carbon double bonded to an oxygen, like an aldehyde, but also an OH group. This hydrogen here can be easily donated, hence they act like an acid because they can donate a hydrogen ion. When they do that, they form a carboxylate ion, which is the next one I've got down here. So when you have it in the acid form, it is an anoic acid. Here's a common carboxylic acid that we come across. 2 carbons, double bonded oxygen OH, so 2 carbons, so it's ethanoic acid, more commonly known as acetic acid, which is the acid which is in vinegar. The carboxylate ion I just sort of talked about there, then the ending becomes anoate. So here is ethanoic acid. After it's donated a hydrogen, it forms the ethanoate ion, probably more commonly known by its common name, acetate ion. We'll get into esters. We don't need to know a lot, but I just want to briefly, it's going to be important what we talk about on the next slide a little bit, but they have, like this carboxylic acid group, but it's in the middle of a chain, a bit like the aldehyde was in the middle of the chain. These are often the the sweet fruity smells that you smell from fruits and baking fresh bread and that sort of thing. We will make in the lab. There is a video up on my YouTube channel if you want to watch it, but we should hopefully do this in the lab next year. We will make this ester here. It's got this OC double bond O in it. 3-methyl-butyl ethanoate, it's called. You don't need to know how to name these this year. That's the characteristic smell of bananas. Next we get into our nitrogen-containing functional groups, and we have the amines, which have a nitrogen in them, and then either hydrogens coming off that, or it could be other alkyl chains. There's different types of amines. Again, we'll go into the detail of that next year. But just one example here, this chemical here, I've done the skeletal structure just to fit it in. 1,4-butane, and because there's 2 amines, we say butanediamine. This is more commonly known as putrescine. It is a chemical that is given off by decomposing bodies, also often responsible for bad breath. Also found in semen and gives semen its characteristic smell. Finally, amides. Amides are really important in biology. They contain a carbon double bonded to an oxygen, then a nitrogen link, if you like, a bit like the esters, but because the nitrogen needs to share one more electron, there's a hydrogen usually attached. We don't really need to know about naming these this year, but that's just there for completeness. So these form the polypeptide links between amino acids in proteins. So whenever you've got proteins, which is basically what our flesh and blood is made of, they are made of amino acids. The amino acids are joined together by these peptide or amide links. So they're really important in biology. Just drawn here, this is an amino acid here. I haven't labelled this. We don't really need to know about it this year, but I think it's worth saying. An amino acid has an amine group at one end. That's where the amino, I guess, comes from in the amino acid. And at the other side of it, it has this carboxylic acid group. So amine acid, amino acid, and then they basically, what makes different amino acids different is what's attached here, where that R is. You can have different alkyl, different hydrocarbon chains attached there. And there's basically 20 amino acids that make up all proteins in all living things found on Earth. So that probably summarises all of the functional groups that we really need to know about. And probably the most important functional group is the alcohols. And we want to just talk a little bit more about the alcohols. This isn't explicitly mentioned in the what the SACE board says we need to know, but it is covered in the book, and I think it is so important that I put it even though it's not absolutely explicitly there in this part of the course, but it does relate to some stuff we did earlier. Anyway, what am I talking about? The physical properties of the alcohols. So the alcohols contain a polar OH bond. This OH bond here in the alcohol is polar. Because it is polar and it's oxygen-hydrogen, which is one of those special cases, it can hydrogen bond. Hydrogen bonding is the strongest secondary interaction that we can have. Therefore, alcohols will tend to have higher melting and boiling points than alkynes of similar molecular mass. So just an example here of this, propane, here molecular mass of about 44, ethanol, molecular mass of about 46. So they're quite similar. The boiling point of propane is minus 188. The melting point of propane is minus 188 degrees. Ethanol is minus 114. So minus 114 is much higher than minus 188. And the boiling point of propane, minus 42 degrees. So it's a gas at room temperature. ethanol, boiling point of 78 degrees. So it's a liquid at room temperature. So that is because of the hydrogen bonding between these polar OH groups. This polar OH group also means alcohols tend to be soluble in water because water is a polar solvent and likes to dissolve in likes. So yeah, at least the smaller alcohols tend to be soluble in water. I'll talk about the larger alcohols in a sec. Now, as the length of the alkyl chain increases, melting point and boiling point increase as molecular mass increases and the strength of the dispersion forces increases. So I haven't got the data here, but if we compared ethanol with 2 carbons with hexanol with 6 carbons, hexanol will have a much higher melting and boiling point because the dispersion forces between the non-polar part of the chain will be much larger. There'll be basically the same amount of hydrogen bonding, so that will lead to it having a greater melting point and boiling point. However, as you increase this chain length, the solubility will decrease because overall the molecule will become more non-polar. So if we have 2-propanol here, also known as isopropyl alcohol, used a lot in hand sanitizer and in sanitizing little swabs for like when you get an injury or a needle or something like that. Also used extensively for cleaning. Dissolves well in water. Only 3 carbons long. So overall, it's reasonably polar. If you go to hexanol, double the amount of carbons, much longer non-polar section compared to the polar OH group. So overall, it becomes more non-polar in nature. Therefore, it will not dissolve. It's not soluble in water because it's more non-polar. Water is polar, and we know likes only dissolve in likes. So that summarizes the functional groups we need to know about and gives us a look at some of the physical properties of alcohols. And as I said, not really, some of this isn't in the curriculum statement, but I think important to help put everything into perspective. And this physical property stuff is stuff we covered earlier in the year when we looked at secondary interactions. So SACE really says there's only one important reaction that we need to know about, at least for now, about the functional groups, and that is about the addition reactions of alkenes. Now, in one of the subtopics coming up, we're going to look at polymers and how polymers are made, and these addition reactions are important for making polymers. I think that's why they put this in as an example here, as opposed to a whole number of other reactions which are also important and that we particularly look at in Year 12. But I'm going to go again a little bit deeper so you can get some context on where and why we use this reaction. This chemical that I've drawn up at the top here is an example of a triglyceride. Triglycerides are essentially triesters. They have 1, 2, 3. So that's why I talked about the ester group in the last slide. They have these 3 esters in this general structure. They are what we commonly know as fats that we get from animals. The fats that we get from animals are solids at room temperature, and they are saturated, so they contain no alkene groups. This triglyceride here contains alkene groups here, so it wouldn't be an animal-based one. It wouldn't be a solid at room temperature. It would more likely be an oil that would be derived from a plant, like canola oil or vegetable oil. It would be a liquid at room temperature, and it would be unsaturated because it contains these alkene double bonds. Now, earlier on, we talked about soaps somewhere when we talked about solubility. One of the ways they make soaps, and again, this is a little bit off task, but they break these triglycerides. So they break the triglyceride through there, and then it basically forms a carboxylate ion. So again, I talked about the carboxylate ion on the previous slide. This carboxylate ion has a charged end. We tend to call that the charged head. So that charged head will interact really well with water. Then it has this really long non-polar tail that will interact really well with a non-polar substance like an oil or grease stain. And these these carboxylate ions that form from breaking the triglycerides are what is used as soaps to make the micelles to help things dissolve that we talked about earlier on in the solubility topic. However, that's not related to the addition reactions. The test for an alkene is that we add bromine and we see if we get what's called addition of bromine across the carbon-carbon double bond. So, and this is a test that is done to determine whether we have saturated fats or unsaturated oils, or in terms of oils, to determine how unsaturated they are. Generally, the more unsaturated an oil is, the healthier it is. So this is a test that's used to determine how saturated oils are. And we take our triglyceride, and I've got a video on this, and I'll put it up as a link that you can watch as well, and hopefully we'll have a chance to do it in the lab as well at some point. And we add bromine to that. Bromine is very orange in colour. And when we add bromine to the triglyceride, it'll basically turn an orange colour because of the orange of the bromine. But when it reacts with the carbon-carbon double bond, it basically breaks this carbon-carbon double bond here, and one of the bromine atoms adds to each end of the double bond, hence addition reaction. It adds to both ends of a carbon-carbon double bond. These chemicals will tend to be colourless. So if we add bromine to an unsaturated fat, we'll see this colour change from orange to colourless. Now, you can almost go down and do like a titration with these and add more and more bromine, and they also use iodine as well, works quite similar fashion. So you can actually, almost do a calculation like a titration to work out how many carbon-carbon double bonds there were in the original molecule. So that is the test for an alkene. We add bromine and we look for an orange to colourless change because of the addition of bromine across the carbon-carbon double bond. Now, this reaction, or a similar reaction, not that reaction exactly, is used to make margarine. Margarine is made from vegetable oil, like up here, contains these carbon-carbon double bonds. They add hydrogen. Now, they need to do this with a catalyst to speed up the reaction and high temperatures and pressures. And again, we learn more about the details for this reaction next year. But in simple terms, you can hopefully understand this hydrogen adds across the double bond. One of these hydrogen atoms, one hydrogen atom from H2 adds to one carbon, the other one to the other carbon, and we get basically, it becomes, if you like, more saturated. There becomes less alkenes present in the triglyceride. Because there are less alkenes present, that tends to cause the melting point to rise, and that's why we can take vegetable oil, add hydrogen in an addition reaction, and turning it into a more saturated, so it's still unsaturated, but it's more saturated than it naturally was, triglyceride, and then it will be a solid at room temperature so that you can spread it on your toast just like you would do with butter that was the precursor to margarine. Personally, I prefer margarine, but I know there's some people who still much prefer their animal-based fats from the cow's milk that's used to make butter. I prefer my breakfast spread made in a chemical factory that was originally grown from plants. I'm not really sure which of those is better for you, but that's not the point of this course. Okay, so that sums up what we need to know about the various functional groups and some of the reactions of those and some of their properties. In the next episode, we'll have a look at another type of reactions involving hydrocarbons, and that is combustion or burning them. Cheers.